Welcome to This Explainer. Today, we're going to do something super practical. We're going to train your eye to visually decode the exact physical patterns of atrial fibrillation across a variety of medical readouts. You know what this condition is in theory, but spotting its signature right there on a page? That's a whole different ballgame. By the end of this session, you'll be able to look at complex medical grids and instantly spot the vital clues hidden right there in the lines.
So let's just dive right into it. We talk about irregular heart rhythms all the time, right? But what does atrial fibrillation actually look like on paper? How does this specific condition translate into literal lines, spikes, and grids on a readout? Well, that is exactly what we're going to unpack today, starting from the absolute basics and working our way all the way up to dense, real-world clinical charts.
Section 1. The core visual pattern. Let's lay down some baseline rules. Take a look at this clean red line tracing on the stark white background. It's perfectly labeled atrial fibrillation right down at the bottom. What's great about this specific image is how it isolates the core anomalies we need to train our eyes to look for. Because there are no distracting grid lines or extra medical data in the way, we can focus literally 100% of our attention purely on the geometry of the heartbeat itself. Okay, breaking this down, there are two golden rules you've got to master here. First, just look at those tall vertical spikes. Notice how the gaps between them are completely uneven? There's absolutely no steady, marching rhythm here, which is exactly what you'd see if the heart was beating effectively. Instead, the spacing is, well, it's completely unpredictable. Second, look at the space connecting those spikes. Instead of a nice, smooth, flat resting point, we see these constant, jagged squiggles. In physical terms, that's literally a heart quivering chaotically instead of giving a strong, organized pump. So remember these two elements, the unpredictable spacing between those highest peaks and that jagged, squiggly baseline. They are your absolute keys to spotting this condition. Moving on to Section 2, reading clinical grids. Time for some real-world patterns. We've nailed the foundational rules on a highly simplified, clean, white graphic, which naturally brings us to our next question. How does this look in an actual clinical setting? Because it's one thing to spot the pattern when it's hand-drawn for you in bright red ink, but what happens when we throw in the intimidating density of a standard clinical readout? Well, it looks exactly like this. The stark shift to this massive, dense pink grid might seem a bit overwhelming at first glance, I know. We've got 5 separate horizontal rows of black clinical tracings, all crisscrossed by thousands of tiny pink squares. But here's the trick. Don't let the grid itself distract you. I want you to focus closely on the black ink spanning right across it, because the exact same foundational patterns we just learned, they're hiding right there in plain sight. To read a multi-row grid like this without panicking, just follow these exact steps. Step 1. Isolate a single horizontal row. Just pick one, let's say the middle row, and completely ignore the rest of it. Step 2. Anchor your eyes on the tallest black spikes in that specific row. Step 3. Visually measure the gaps between those spikes. When you do this, boom, you'll instantly confirm what we saw earlier. The distance between them is constantly shifting. The spacing is undeniably uneven. And if you trace the line between those irregularly spaced spikes, you're going to see those same chaotic, squiggly baselines popping up again all across the grid. All right, Section 3, fine fibrillation, spotting those nuanced clues. This side-by-side comparison brilliantly illustrates the contrast. Over on the left, we've got our original image, the obvious chaotic squiggles of the red tracing. But look at the clinical tracing on the right, showing a single row. Notice the spaces between the tall, irregularly spaced spikes. That chaotic, jagged line we saw on the left has shrunk down so much on the right that it appears almost completely flat. The irregularity in the distance between the tall spikes is definitely still there, for sure, but those squiggles between them, they're incredibly subtle. Now, check out the literal text printed right above that tracing. It explicitly labels this almost flat variation as atrial fibrillation fine, noting the amplitude is less than 0.1 millivolts. So this is the strict definition of fine fibrillation. It's a presentation where the jagged baseline between spikes is extremely small, specifically measuring less than 0.1 millivolts in height. Your eye really has to be trained to catch this, because at a casual glance, that baseline looks perfectly smooth. But structurally, the exact same chaotic quivering is happening, it's just manifesting on a micro scale. Also, if you look really closely at that same right-hand image, you can see the tiny notation lead eye right at the very top left corner of the grid. This gives us the exact clinical context for this specific row of tracing. It lets the reader know precisely which perspective of the heart's electrical activity is actually being shown. So the crucial point here is understanding how these outputs are actually formally governed. If we look at the bottom text of that third readout, we see it's strictly calibrated. As our table here highlights, it's operating at a speed of 25 millimeters per second and a scale of 10 millimeters per millivolt. This standardized calibration is literally the only reason we can definitively measure that the fine fibrillation is indeed less than 0.1 millivolts. Without these standard grid measurements dictating exactly how much time and voltage each box represents, well, we wouldn't be able to accurately analyze or compare these incredibly subtle variations at all. We've covered tremendous ground today. Having trained your eye to jump from a simple, isolated red schematic all the way to analyzing sub-millimeter technical measurements on dense clinical grids, you now possess an incredibly powerful analytical toolkit. The structural chaos of this rhythm leaves a very specific footprint, whether that's massive, jagged squiggles or an almost imperceptibly flat line between uneven spikes. So I'll leave you with this final thought. The next time you see a complex medical grid flashed on a screen, will you be able to cut through the noise and instantly spot the irregularity hidden right there in the lines? Thanks for joining me for this explainer, and keep your eyes trained on the details.